So Unit 3 is focused on solving a set of linear algebraic equations. So what is a linear algebraic equation? It's basically an equation with variables, all right, such as x, y, or x, y, z, multiplied by some coefficient. But all of these variables are always to the power of 1. So because they're to the power of 1, this is why we call it as a linear algebraic equation. So you could have 2 of them, you could have 3 of those variables, or you could have, many or n number of variables. All right. So the whole point of these equations is to represent a system, and we're trying to solve, variables within that system, so we understand or basically find a solution to a problem that we have. For example, if we have some type of water tank, and the water tank has a certain level of water, certain pressure, certain temperature, certain volume, certain material cost, we can put all these variables into this equation and then have different equations representing maybe the profit, representing maybe the quality of the water, different equations representing different things. And all of these are dependent on, say, maybe the temperature that we keep the water at, or, maybe if you want to cool the water, it's going to cost you more money. Or if you keep it not cooled, then it's less money, but the quality might be less, right? So all of these variables can be represented in equations. You solve the equations and you find out what's the best water temperature I should have. What's the pressure that I should have? Maybe what material should the tank be made of? All these things you can solve for using these equations. All right. So in this unit, we're going to look at different ways of solving these linear equations. First, we're going to today start with Cramer's rule and then Gauss elimination. Then we're going to move on to LU decomposition, matrix inversion, and then in the end, we would look at the numerical way of solving them, which is the Gauss-Seidel and Gauss-Seidel with relaxation. So all of these methods you've probably seen from algebra if you took algebra. If you didn't, it's okay, because I'm going to go through the details here. And hopefully, if you have any questions, obviously you can ask me. The first method I'm going to present, which is not on here, is just the graphical approach, which is the basic method. And you won't be tested on the graphical approach, but just showing you in general what is the graphical approach. So if we have 2 equations, such as these 2, and every time we have a set of equations, right? If I have 2 unknowns, I need 2 equations. If I have 3 unknowns, I need 3 equations, and so on. So the number of equations has to equal the number of unknown variables that you're trying to solve for. So in this case, I have 2 unknowns, x1 and x2, and then a11, and all these are coefficients which should be known, all right? And I'm trying to solve for the values of x1 and x2. So the simplest approach is the graphical approach. You rearrange each one of these equations to solve for one of the variables. In this case, I'm solving for x2. And then you graph that equation, these 2 equations that you came up with, and wherever they intercept is the solution for x1 and x2. All right, so that's the simplest approach. You draw, this is one line, this is another line. They intercept at 3 and 4. So x2 is 3 and x1 is 4. All right, so that's the simplest way to do this. Another way of doing it, which is not necessarily graphing it and looking at where is that value where they intercept, is to actually use the equations that you rearranged and make them equal to each other. So if we look back here, we solved for x2 in both of them. So I make both equations equal to each other because they're both equal to x2. Then I solve for x1. Once I know x1, then I can plug it in back to the equation and then solve for x2. So very general approach, which is considered under the graphical method. All right. And we're not going to be really doing this in this course, but I'm just presenting it in here. All right, sometimes when we have these different equations, right, we can have different conditions. If these 2 equations, the solution is impossible, right? Or basically you have two lines that are parallel when you graph it, right? Then there is no solution to the problem. If the two equations are a multiple of each other, so if you look at this equation and this equation, this is basically this equation times 2, right? Meaning that I don't have independent equations. It's basically the same equation multiplied by 2. Then you're not going to have basically a solution, but infinite solutions, all right? Because it's basically the same equation. If you have an ill-conditioned system, it's basically when the slopes are really close to each other, then graphically it's going to be really hard to find the intercept. And even when I use the other methods that we're going to look at later on, you're going to have a lot of rounding error when we do a lot of steps in those methods. Okay, so that's basically the ill-conditioned kind of case. All right, so in terms of linear equations, we can represent them using matrices. So you guys, if you haven't seen matrices, it's okay. I'm going to go over it right now. But essentially, these are three equations with three unknowns, x1, x2, and x3. I can represent this using the format ax equals b, where A is a matrix of the coefficients, right? So if you see here, this is a coefficient, another one. All of these are set in a row for the first equation. Second equation, A21, A22, A23, second row here, and so on. X is a vector of the unknowns. So X would be X1, X2, X3. So if I multiply A by X, I should get B, right? Where B is a vector of basically the side of the equations. So B1, B2, and B3. Any questions on this format so far? All right. So we're going to start off with the Cramer's Rule, which is the kind of simplest way of solving these equations. And in Cramer's Rule, we have to find the determinant of a matrix. So the determinant of an order 1 matrix, where it has only one coefficient, is basically that coefficient. But this is not really useful because we're not really solving any equations. It's just, one value that's in there. If I have two unknowns and basically sets of two coefficients, then I have an order 2 matrix. And in this case, the determinant is A11 times A22, right? Minus A12 times A21. All right. Again, I'm going to do an example to show this this step, but that's the basic one. And in this course, I'm not going to be using, I'm not going to ask you to use Cramer's rule with a matrix larger than 2 by 2, okay? Because it's not a linear algebra course. It's numerical methods. So we want to focus on the numerical methods instead of these methods. But in any case, this is the 3 by 3, just so you know. We can also solve the 3 by 3 and know the determinants of the 3 by 3. But in this case, it's split up into smaller determinants that are easier to solve, right? Which are 2 by 2, where we have, the coefficients A11, A12, and A13 used in the formula to find the determinant of this 3 by 3 matrix, okay? And the way we do this is we use these kind of numbers. So the one here represents the row, and this one represents the column. All right. So what's happening here is if I want to find the D11, I'm crossing out row 1 and column 1, and I'm using this here as D11. So you can see this is the determinant D11. Same thing with A12 here. I'm using this as the row, this as the column. So I cross out row 1 and column 2. So then I'm using A21, A23, A31, A33 in here to solve for the determinant. All right. So you get the point, but essentially we won't be, doing much of this 3 by 3s or Cramer's rule in this course. In terms of once you find the determinant, now we want to solve for the unknown, which is x1, x2, and x3, right? So we kind of have an idea now of what is the determinant. To find x1, you need the determinant a1 divided by the determinant d, which is, so d is for the coefficient matrix A. A1 would be a matrix where you replace the column, okay, with the value that we see here. So in this case, I see a 1 here. So I'm going to replace column 1 with the B vector. All right? So this is B1, B2, B3, and then the rest of the matrix, the coefficient matrix, stays the same. And that's how I get x1. So similarly, for the other ones, x2, I have a2, where I replace the second column with the B vector to solve for x2. All right, and then for x3, I replace the third column to solve for a3 and get x3. Any questions on this so far? All right, so let's do an example. So this is the example here. We're going to do a 2 by 2. These are the two equations, and we're going to solve it together. So this is lecture 3.1. Let's use black here. And this is from slide 13. And this is Cramer's Rule example. All right, so we have two equations. We have 3x1 plus 2x2 equals 18. And then we have negative x1 plus 2x2 equals 2. All right, and the solution, right, for x1 and x2 is basically x1 equals a1 divided by d, and then x2 equals to a2 divided by d. So to start this off, we want to find what's d, what's a1, and what's a2, and from there we can solve for x1 and x2. So in this case, let's start with d. So d is the determinant of the coefficient matrix. So what's the coefficient matrix in this case? Right, 3, 2, minus 1, 2. So, and this is going to equal to, we first multiply the 3 by 2, so the diagonal. So we do 3 times 2 minus the other diagonal, so 2 times negative 1. So we're going to write that down. We have a 2 here, and we have a negative 1. So this is a 6, and then this is plus 2, so we get 8. So this is the determinant of the coefficient matrix. Now we want to find a1, right? And if you remember, a1, we replace the first column with the B vector, right? So how would a1 look like in this case? Right, so we have 18, 2, and then 2 and 2. So you can see that, basically here, we kept these coefficients, and then the 18 and 2 come from this B vector on this right side. All right? Any questions on that? All right. So then we repeat the same thing. We multiply 18 by 2, right? So we go across again this way. And then we subtract the other diagonal, so 2 times 2. Right? So we get here 36 minus 4. So this would be a negative 4 in this case. So 36 minus 4, you get 32. So this is a1. Then we go for a2. In this case, we replace the second column with the B vector. So we have, the original coefficients, 3 and negative 1. Then we put 18 and 2 on the second column. And then we repeat 3 times 2 minus 18 times negative 1. In this case, we have 6, and we have plus 18 on this side, so we get 24. So now we can go back to the equations, x1 and x2, and plug in those values that we found out and find what x1 and x2 are. So in this case, x1 equals to a1 divided by d, which is 32 divided by 8, which gives us 4. So that's x1. And then x2 would be a2 divided by d, which is 24 divided by 8, right? Which gives us 3. So this would be our x2. Any questions? No questions? Straightforward? All right, so let's keep going. So the next method we're going to look at is Gauss elimination, all right, which is basically a method where we try to eliminate basically parts of the equation, so it becomes easier to solve, all right? So let's just get into it here. So if we have the format AX equals B, right? So we have the augmented matrix, which is this format, which is the coefficient matrix combined with the B vector, separated by this line. What we do is we do forward elimination to get these bottom 3 positions equal to 0. And then after that, we use backward substitution or back substitution to solve for x3 from this here, x2 from this here, and x1 from this here. So we'll do an example so it becomes a bit more clear. And if you have questions, please let me know. All right. One thing to note here is these primes essentially mean that these values are not the original values, okay, in this slide. All right. So let's do a board problem. So we're going to solve the following set of linear equations. So we have 3 equations, 3 unknowns, and we're going to transform this into an augmented matrix, do forward elimination, and then do back substitution. All right, so let's close this here. All right, so this is slide 16, and we're doing Gauss elimination. Example, and we have x1 minus x2 plus x3 equals 6, and we have 3x1 plus 4x2 plus 2x3 equals 9, and then 2x1 plus x2 plus x3 equals 7. All right, so what's the first step here? Right, so we're going to do the augmented matrix. And that's going to be the coefficient matrix, right? So we're going to have the coefficients of the first equation, and the second, and the third, all written down. So we have 1, -1, and 1. Then we draw a line, and then we have the value of b after that. Then we close it off. All right, so here we have 3, 4, 2, and 9. And then here we have 2, 1, 1, and 7. This top left value right here is called the pivot. All right, the pivot should not be a value of 0. If it's a value of 0, then the Gauss elimination steps will not work. All right, so we'll get into what we can do in that case, which is essentially kind of rearranging the equations. So we'll get into that in the slides after that, but let's focus on this right now. So our goal, as we mentioned before, is to get these 3 positions equal to 0. All right, so the goal here, is to make these zeros. And how do we do that? We use row operations. All right. Whenever I have a 3 by 3, it only requires 3 row operations to get these to zeros. So I'm going to teach you how you should approach this. And it's a systematic way where you always should do it this way. Because later on, when we do LU decomposition, you have to do it in this kind of algorithm of 3 steps. Okay? So always in forward elimination, so we're going to do here forward elimination. What happens to the first row? Right. So the first row is already, at the goal that we want it. We don't want to change anything with it, right? So it will remain the same. And I'll just say here, basically row 1 is unchanged. Now row 2, in the first step here, for row 2 and row 3, I want to change them using row 1. All right, so this is very key here. You have to use row 1 for row 2 and row 3. And the other key thing here is for row 2 or row 3, okay, I always want to do some type of calculation where row 2 is just plus row 2, right? And we said we want to use row 1, so we're going to have row 1 here. And the main thing that you want to choose is what's the coefficient that goes here. That's the only thing you want to change. So whenever you have a different, basically, matrix, that's the only thing that will change. But R2 will always equal something multiplied by R1 plus R2. Okay? And the same thing will apply for row 3. So row 3 will always be something multiplied by row 1 plus row 3. All right? So now the game is, what should that coefficient be to get a 0 in that first position in row 2? Right, so this would be -3 for row 2, because we have a 1 on top. So if I multiply 1 by -3, plus 3 will get a 0, right? And how about row 3? -2, right? Because we have a 2 here, and again, that's a 1, so that's how we get it. So then we would get a 0 here, and I have to do this calculation, right, for the entire row, right? So we do -1 times -3 plus 4 for the next one. So that would be a 7. Then the next one would be, -3 times 1, right, plus row 2, which is 2. So -3 times 1 plus 2 will give us -1. And then you do that, the same thing with the b here, so you get -9 here. All right? So I'm not going to do all these small steps here, but you could try out the calculations later on. But you need to understand the main concept, which is what I'm covering in this case. So again, here we're going to get a 0, then a 3, then a -1, and then a -1. All right, so now we have one more row operation to achieve our goal of getting these bottom 3 equal to 0. So in this next step, the first 2 rows are going to be the same, so unchanged. So 0, 7, -1, -9, and these 2 here are unchanged from the previous step. Row 3, on the other hand, needs to be modified. And in this case, you always want to use row 2 to modify row 3. All right, so this is going to equal some multiple here, multiplied by row 2 plus row 3. So in this case, because there's a 1 on the left, if I use this row 1, I will change this, right? So that's why we don't use row 1. All right. So in this case, simply to get what the factor is, you look at what the values that we have here. In this case, I have a 3 and a 7, right? So my goal is to get row 2 equal to what? -3, right? And I have a 7. So then I write what I want. I want a -3. And I divide by whatever value I have there, which is 7. Doing that will give me a 0 in that middle section there. So we have already 0 here. We get a 0 here. Then I get a fraction here, -4 divided by 7. Then here I have a -8 divided by 7. So now we're done with the forward elimination. Next step is to do back substitution. Any questions so far? All right. So in back substitution, you can simply, use the equations that are set up here, like ax equals b. So we're looking at ax equals b, right? So we have, in this case, in the last row, right, it would be 0 times x1 plus 0 times x2 plus -4 divided by 7 times x3 equals -8 divided by 7. All right? So this is kind of the full equation, but typically we wouldn't write any of this, right? We would just write the last part and then just solve. One other approach, which is kind of like a quick way of doing this, you write, instead of doing this whole equation, you can just simply write x3 equals to 1 over whatever the coefficient is. So in this case, the coefficient is -4 divided by 7, multiplied by b, which is -8 divided by 7. Okay? This will make sense when I look at the other values as well. Like, for example, if I'm looking at x2 in this case, I'm going to look at 1 divided by the coefficient, which is what in this case? For the second row, 7, right? So I do 1 divided by 7 multiplied by b, which is -9, minus whatever comes on the right side. So in this case, I have a -1. So minus -1 times what? x3, right? This whole column here would be always multiplied by x3. This column here is always multiplied by x2. Okay, and then the first one is x1. All right. So then I can do this math, but first I have to solve for x3 before I do x2, right? And then also in the last step, if I want to do this same kind of algorithm of writing this down, we would say x1 equals to 1 over what? 1 times what? Just a 6, right? 6, and then we do minus -1, all right? So -1 times what? x2 minus the next coefficient, which is 1, times x3. All right? So then we solve the first one. The first one will be basically 7 over 4 times -8 over 7, where we basically cancel out the 7s, right? Which will give us 2. I take this 2, I plug it in here, right? And then I solve, and then I get -1. So this would be my x2. This is x1. And then again, I use x2, which is here -1, and x3 is 2. And I solve the last one to get 3. So this is, sorry, this is x3 here. And this is x1. So in conclusion, for this problem, we can say, therefore, x1, x2, x3 is equal to 3, -1, and 2. So that would be the solution to this problem using Gauss elimination. As I mentioned before, one of the kind of pitfalls of this method is if I have a 0 in the pivot position, so this position here is a 0, or if I have a 0 in the diagonal also, during the steps that you do, you get a 0 in the diagonal. That will basically break this method. So to avoid this, or to kind of go around this problem, what we do is we call it pivoting, okay, where we switch the rows. And if I'm switching the rows, we call it partial pivoting. If I'm switching also the columns, so if I'm switching this column with this column, then I call it complete pivoting. All right. So all of that is summarized kind of in this kind of slide here, where we say the row can then be switched. So the largest element is the pivot in the pivot position or the element, and this is called partial pivoting. And then if I switch the columns and the rows, then I call this complete pivoting. So one important thing to note here, if I'm switching the columns, so if let's go back to this slide. If I switch column 1, this column here, with this column, then also the x's are also switching. Okay, so instead of the x vector, right, the x vector initially was x1, x2, x3. If I switch column 1 with column 2, then I have to switch x2 and x1. Okay, so if you ever do have to do that, then make sure you follow this when you're solving, right, to keep track of what is the x1, what is the x2, and what's the x3. Any questions on this one? All right, so the last couple slides here. Tridiagonal systems. So this is basically a system where if I build the coefficient matrix A, I have values in the diagonals, the 3 diagonals, and everything else is a 0. So this type of system is really easy to solve using Gauss elimination, right? Because most of the matrix is already a 0. So it's really easy to solve. So that's kind of what this slide's saying. The other kind of approach, instead of doing, forward elimination and then just back substitution, is to continue doing row operations until you get everything as zeros except for the diagonal. This is called Gauss-Jordan elimination. All right, so basically you would get a matrix that kind of looks like this, where you have zeros here, and then you just have values across the diagonal. They could be also ones if you continue the row operations. Okay, we're not going to really go into this in this course. All right, but this is kind of just showing you what Gauss-Jordan elimination looks like. All right, so we have a few minutes left if you want. I don't know how many minutes. We have no time, actually. All right, so at home, you can try this set of equations. I have the answers written down on the bottom right. So try this out, and then you can use either Gauss-Jordan or use Gauss elimination just to practice and make sure you understand what we've covered in this lecture today. And I also recommend repeating the Cramers Rule example to kind of make sure you understand that in case this lecture wasn't relevant.